In this video, I'm going to talk about the radio noise that I was picking up with the ECG and talk about how to use filtering to get rid of it. The setup for this video looks like this. It's pretty similar to last time, except instead of having two resistors, one on each branch, it only has one, and that's on the shared ground reference. I used this setup in a video a while back trying to pick up the cable rubbing noise, but ended up picking a whole bunch of radio up instead, so I'm going back to this to test the RF filtering. So now to replicate the original problem, let's just turn this on and start recording. So I've noticed it only really picks up radio when I'm actually touching the wires, so it's me acting as the antenna, but it still picks up plenty of radio, which we can listen to.
Insurance company is now offering affordable term life insurance.
Both of these loops are right up next to each other, and I was touching both of them at the same time. So any RF that this was picking up was common mode, so it was the same at both of the inputs. And it was still getting through the instrumentation amplifier, which is supposed to have high common mode rejection. So what's going on here is my instrumentation amplifier might have good common mode rejection at low frequencies, but it has really bad common mode rejection at high frequencies. So let's talk about why that is. Now, if you remember with the instrumentation amplifier that I'm using, I have two inputs, one for each end of the differential signal, and both of those signals go through some gain before one gets subtracted from the other. And in order to get good common mode rejection, the gain of both of these paths needs to be matched really well to each other. And also the time delay needs to be matched really well to each other, which I'll talk about in a bit. Now, when we build an op-amp circuit, we usually assume that the op-amps have infinite gain, and then we use some external components like these resistors to artificially limit the gain by giving it negative feedback. But op-amps also have their own internal parasitic components which limit its own gain by giving negative feedback inside the op-amp itself. And this is usually capacitive, so as the frequency gets higher and higher, it gets more and more negative feedback and it limits its own gain. And that's what this plot here is trying to show. Here I show the gain of the op-amp circuit over frequency. So this horizontal dotted line here shows the gain limit set by the external components, which does not depend on frequency if they're just resistors. But the gain is also limited internally, which I show with this diagonal dotted line, and the gain gets lower and lower as the frequency gets higher and higher. So this solid line here shows the total gain of the op-amp circuit, and it's going to be limited by whichever one of these limits has lower gain. So you can see that for low frequencies, we control the gain of the op-amp circuit with our external components. But when the frequency gets past some corner frequency or a cutoff frequency here, then the op-amp circuit's gain is limited by its internal components. And the important thing here is that although we can control these external components to make the gain whatever we want, after it gets past this cutoff frequency here, we can no longer control the gain of this op-amp circuit. Now in my inamp circuit, I have two paths that I need to worry about. So even if I set the external gain limit the same with the same external resistors, the two op-amps might have different internal components, which give it a different internal gain limit. So for low frequencies, I can still be pretty well matched as far as gain goes, but at higher frequencies, they might have pretty different gains. Now, if I use the common mode adjustment knob on my circuit to match the gains at high frequency, then they become mismatched at low frequencies. So when I'm dealing with both high and low frequency signals, when I'm trying to balance the gain between the two paths, I'm sort of damned if I do and damned if I don't. I also mentioned that the time delay between the two paths needs to be matched. I haven't mentioned this in previous videos because there I've only been worried about low frequency signals where it doesn't really matter all that much. But now it does matter with high frequency signals like radio. So here again I have an overlay which represents the other path in the op-amp circuit. So the bottom sheet of paper represents one of the signals that's coming in, and the top overlay represents the other signal that's coming in, which needs to be subtracted from it. So now let's see what happens when one of the signals is delayed just a little bit. Here the high frequency and low frequency signals have been delayed by the same amount because I shifted the overlay by the same amount, but you can see the low frequency signal has a pretty small difference between the two signals after it was shifted, and the high frequency signal has a really large difference between those two after it was shifted. So because of this, even if I could get the gains perfectly matched between the two channels, if the time delay was even mismatched by a little bit, that's going to hurt really bad for these high frequency signals. So getting an inamp like this to have good common mode rejection at high frequencies and low frequencies at the same time is just intrinsically difficult to do. So the only thing to do is to put some sort of a filter on the front end to make sure that I don't actually get any high frequency noise going into the circuit. And bad common mode rejection is not the only way that RF can wreak havoc on op-amp circuits. Remember that the signal was not coming out of my circuit as RF, it was coming out as audio, which means that some nonlinearity inside the circuit was demodulating it. So if the nonlinearity was the type that rectified the signal, then the signal coming out has an average value that's no longer 0 volts, which means it has a DC offset on it. So RF signals getting in can also be a source of unwanted DC offsets. And also, signals can jump from one amplifier to another within a circuit. So here I have the schematic of one of the amplifiers from an LM324. They bias all of the amplifier stages with current sources, but the current sources are not going to be perfect, and they're going to be even less perfect at high frequencies. So as the input voltage goes up and down, the current draw from the supply is also going to go up and down a little bit with the signal. And the power supply here is connected through some wire which is not going to be perfect, so it has some resistance to it, which means that as that current change goes through the resistor, it's going to generate a changing voltage drop over that resistor. And again, this is going to get even worse at high frequencies because the wire also has some inductance to it, and if the frequency is high enough, the skin effect starts becoming important and the resistance increases. So now you have your signal voltage actually showing up on top of the power supply, and this power supply is also connected between this amplifier and all the other amplifiers on the chip, which means now their power supplies are being modulated with your input signal, and all sorts of bad stuff happens. The way to get around this is to add a decoupling capacitor between the power supply and ground, so that instead of being forced to go through this resistance, any radio frequency current can just slide to ground through this capacitor. Eventually I'm going to add these capacitors in, but for now I'm going to leave them off. I want the RF to wreak as much havoc in my circuit as possible because that's how I know it's there. And that's also how I'm going to be able to tell how well my filtering is doing. I built a couple of different filters to test. They're both just basic RC low-pass filters with the same cutoff frequency of about 16 kilohertz. The difference is one is designed to reject common mode signals, and the other one is designed to reject differential signals. Eventually I'm going to combine them to try and reject both, but for now I just want to play with them and see what happens with each. The common mode filter is just two single-ended RC filters. It'll filter both common mode and differential signals, but for differential signals, these two capacitors show up in series, so the capacitance gets cut in half and it only filters half as well. With the differential filter, however, the capacitor here only shows up for differential signals, so common mode signals don't get filtered at all. Now, neither of these filters are perfect. The differential filter is still going to let through all of the common mode signal, which I'm still going to have a problem with at RF. And the common mode filter doesn't filter differential signals as well, and if there's any imbalance in these two filters, it'll take a common mode signal and turn it into a differential signal. But just to see what happens, I'm going to try them each individually before I combine them. Also, in the description down below, I've added some links to some good papers about RF filtering for inamps. So now I got to test it with the filters, but first I'm going to try it without a filter again, just as a control. Let's go ahead and put that on and record. So that's about how much radio noise I get out of it without any filtering on it. Now let's see how this does with the differential filter. So not too much difference there. And now with the common mode filter. Look at that, I didn't get anything out of it. So it's pretty clear here that the differential mode filter really did not do any better than no filtering at all, and the common mode filter was really all I needed to suppress all of that RF noise at the input. I was worried about these two filters being mismatched and then creating a differential mode signal at the input, but it looks like the cutoff frequency of these filters was so much lower than the radio frequency that the radio frequency signals were already attenuated so heavily by the time they got through that any imbalance didn't really matter anymore. But just to make sure I don't have any imbalance problems at low frequencies, I'm going to replace these 5% tolerance resistors with 1% tolerance resistors. And I'm also going to add another capacitor across both of the inputs to act as a short circuit for any high frequency differential mode that gets created by any filter imbalance. But the papers that I linked to down below describe that pretty well. So I'm going to finish up this video, and then in the next video I'll put it all together, make sure that it still works at low frequencies, and then I'll also try out the audio cable as the electrode cable.